Welcome, curious minds, to the deep dive.
Great to be diving in.
So, here's a thought to kick us off. What if the very fabric of reality, the basic rules of the universe, weren't quite as, constant as we assume? Imagine a universe where the speed of light kind of flickered, changed from one moment to the next. Or maybe gravity occasionally decided to take a day off.
That would be chaotic, to say the least.
Exactly. Thankfully, our universe seems to operate on incredibly stable principles. And that's our topic today. We're taking a deep dive into the fascinating world of fundamental constants. Now, these aren't just abstract numbers you find in physics textbooks.
Not at all. They're really the unchanging pillars holding up our physical world. They dictate everything from, how atoms hold together to how entire galaxies form.
And our guide for this exploration is the insightful book, The Natural Laws of the Universe, Understanding Fundamental Constants by Jean-Philippe Bouzan and Bénédicte Leclerc.
A really excellent source for digging into this.
Our mission today is to unpack what these constants actually are, how humanity painstakingly discovered and measured them over centuries. It's quite a story.
It really is a journey of discovery.
We'll look at why their stability is so crucial and also touch on what the cutting edge of physics is still trying to figure out about them.
Yeah, the story isn't over yet.
So get ready for some mind-bending facts and some fascinating history that should really deepen your understanding of the universe's deepest secrets.
Let's do it.
Okay, so let's start at the beginning. We often talk about the laws of the universe, but what exactly makes something a fundamental constant in physics? What sets it apart?
That's the perfect place to start because the definition itself is, it's foundational, isn't it? A fundamental constant is a quantity that, by its very nature, maintains the exact same value. Always.
Regardless of conditions.
Regardless of varying conditions. Parameters.
Right.
Anything. It's independent of your specific measurement setup or the particular variable you might be studying. Think of it as like an unchanging, irreducible ingredient within a physical theory.
Okay.
A numerical value that describes some intrinsic property of the universe itself. It just is that value.
Can you give us some examples, things people might have heard of?
Sure. The most famous is probably the speed of light in a vacuum. Call it C. You've definitely heard of EIC, that's C.
Right.
Then there's the gravitational constant, G. That's the one that tells you how strong gravity is, how strongly masses pull on each other.
Okay, Newton's constant.
Exactly. Planck's constant, HA, is absolutely crucial for understanding the quantum world. It basically defines the smallest possible packet or quantum of energy or action.
The quantum realm, right?
Then there's the elementary charge, that defines the electric charge of a single proton or the negative charge of an electron. It's like the fundamental unit of charge. You can't divide it further.
Got it.
And even the masses of fundamental particles, like the electron and the proton. Those are considered fundamental constants too, because they're intrinsic properties that, as far as we know, just don't change.
So why should we, or you listening, really care about these numbers? They sound a bit abstract.
Well, they sound abstract, but their impact is incredibly profound. They are literally the bedrock upon which all our understanding of the universe is built.
How so?
Well, think about it. They dictate the stability of atoms, how electrons orbit a nucleus, how strongly they're bound. That depends on constants like the elementary charge and Planck's constant. And that, in turn, defines all of chemistry, all of matter as we know it.
Okay, so chemistry relies on them.
Absolutely.
Yeah.
They also set the strength of the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces. They make sure interactions between particles happen in a predictable way.
Right.
And they even dictate the very structure of space and time as we perceive it, especially the speed of light.
Wow. So the core idea is their value is critical.
It's absolutely critical. Here's the kicker. If even one of these values were slightly different if C were a tiny bit faster or G a bit weaker, or the fine structure constant changed, just a fraction, the universe you inhabit simply wouldn't exist as it does. Maybe stars wouldn't form, or they'd burn out instantly. Maybe atoms wouldn't be stable. Life, certainly as we understand it, would be completely impossible. They are truly universal constants that shape everything.
That's quite a statement. Our existence hinges on these precise numbers. And, it's easy to take them for granted today, assuming we always knew them.
Right.
But they're actually the result of centuries of scientific struggle and discovery.
Yeah.
Can you walk us through how humanity even began to figure these things out?
Absolutely. And it is a journey. It's a story of scientific evolution, really, moving from just watching the stars to doing complex experiments. It's a testament to human curiosity, I think, and just persistent inquiry.
It's about this gradual revealing of the underlying unvarying principles of the cosmos. We went from describing what happens, like planets moving, to understanding why it happens, and then, crucially, putting a number on that why.
So where does that story begin, ancient Greeks?
We could go back further, but a really key starting point for quantifying these laws is with celestial harmonies, specifically Johannes Kepler's laws of planetary motion. This is before Newton gave us the why, the force.
Okay, Kepler, early 17th century.
That's right. He was working with this incredibly detailed astronomical data collected by Tycho Brahe, just phenomenal observations for the time. Kepler spent years, literally years, sifting through it, looking for mathematical patterns.
And he found them.
He found three huge ones. First, planets orbit the sun in ellipses, not perfect circles, which was a big break from tradition. And the sun isn't at the center, it's at one focus of the ellipse.
Right, not circles. Got it.
Second, his law of areas. A line connecting planet and the sun sweeps out equal areas in equal amounts of time, which basically means planets move faster when they're closer to the sun and slower when they're farther away.
Okay, that makes intuitive sense.
And his third law, the harmonic law, is maybe the most relevant here. It states that the square of a planet's orbital period, how long it takes to go around the sun, is directly proportional to the cube of the semi-major axis of its orbit, which is basically its average distance from the sun.
A specific mathematical relationship?
Exactly, a consistent mathematical relationship that held true for all the known planets. The core realization here was immense. These were descriptive laws, yes, but they were quantifiable, and they seemed universal, at least within our solar system. They laid the groundwork for Newton to ask why they moved this way, hinting that some underlying force, maybe with a constant strength, was at play.
So Kepler set the stage, described the how, but before Newton could explain the why of gravity, there was another giant leap in understanding motion itself, wasn't there? From Galileo.
Precisely. Galilei. His insights were absolutely revolutionary because they completely challenged the old Aristotelian views on motion. Aristotle basically thought things needed a constant push or pull to keep moving.
Right, that objects naturally wanted to be at rest.
Exactly. Galileo turned that on its head. His great principle was essentially that motion is nothing, meaning uniform motion in a straight line. It's fundamentally indistinguishable from being at rest if you're observing it from within a closed system.
That sounds counterintuitive. How did he explain that?
His thought experiment, the ship's cabin, makes it clearer. Imagine you're inside a windowless cabin on a ship sailing smoothly on calm water at a constant speed in a straight line.
Okay.
Now, inside that cabin, maybe a butterfly flits around, or you drop a ball and it falls straight down into a bucket. Or water drips from the ceiling into a bowl. Galileo argued that the butterfly wouldn't get slammed against the back wall. The ball would fall straight down, not drift backward. Everything inside that cabin would behave exactly the same way, whether the ship was moving steadily or tied up at the dock, completely stationary.
So you couldn't tell you were moving without looking outside?
Precisely. There's no experiment you can do inside that cabin to detect the ship's uniform motion. Motion in that sense is relative. This established the concept of inertial frames of reference frames, where objects at rest stay at rest, and objects in motion continue in uniform motion unless acted on by a force.
And that's fundamental for physics.
It's a bedrock principle. It was crucial for Newton, and later Einstein built his theories of relativity right on top of this Galilean idea of relative motion within inertial frames. It completely changed how we understood motion and rest.
Okay, so we have Kepler's laws describing planetary motion, Galileo's principle of inertia. The stage is set for Newton.
Absolutely. Isaac Newton arrives, deeply inspired by Kepler's work on how the planets moved and Galileo's insights into motion itself. He wanted to know why. Why do planets follow these elliptical paths? Why does an apple fall to the ground?
And he suspected they were related.
That was his genius. He sought to explain planetary motion and link it to everyday phenomena here on Earth. This quest culminated in his masterpiece, the Principia Mathematica, published in 1687. A landmark work.
And in it, the law of universal gravitation.
Exactly. He proposed that every particle in the universe attracts every other particle. The force is directly proportional to the product of their masses. More massive things pull harder and inversely proportional to the square of the distance between their centers. Further apart, weaker pull.
The inverse square law.
The famous inverse square law. And the equation we usually see is F equals G times M1 times M2 divided by R squared. F equals G and 1 medi 2 R2.
And there it is, G, the gravitational constant.
Our first really big fundamental constant, right there in the equation. G quantifies the intrinsic strength of the gravitational force. Now, Newton understood the relationship perfectly, mass, distance, force, but he didn't actually know the numerical value of G.
He knew how it worked, but not the exact strength.
Right, but the conceptual leap was audacious. He claimed the very same force pulling the apple down was keeping the moon in orbit around the Earth. He unified terrestrial and celestial mechanics, shattering that old philosophical divide. That was revolutionary.
So how did we get the value for G? You said Newton didn't have it.
Measuring G was incredibly difficult. Gravity is actually surprisingly weak between everyday objects. You don't feel the gravitational pull between you and your chair.
Not really, no.
It took over a century after Newton's work. In 1798, Henry Cavendish performed his famous experiment using a torsion balance. It's ingenious, really.
How did it work?
He suspended a light wooden rod horizontally by a thin wire. On the ends of the rod were two small lead spheres. Then, he brought two much larger lead spheres close to the small ones, one on each side.
Okay.
The tiny gravitational attraction between the large sphere and the small sphere on each side caused the rod to rotate slightly, twisting the wire it was suspended from by a minuscule amount.
Tiny twist.
Incredibly tiny. But by precisely measuring the angle of that twist and knowing how much force it took to twist that specific wire, its torsion coefficient, Cavendish could calculate the gravitational force between the spheres. Since he knew their masses and the distance between them, he could plug everything into Newton's equation and solve for G.
Wow. That sounds painstaking.
It was famously painstaking, but it worked. It not only gave us the first accurate value for G, but it also beautifully demonstrated the universality of gravity. The same G applies to lead balls in a lab as it does to planets and stars. It truly confirmed Newton's vision of a single universal force.
Okay, so that's gravity and G. Let's pivot now to another fundamental force, and maybe the most famous constant, light and C. Its nature was debated for ages, wasn't it?
Indeed. The story of light is a perfect example of how science progresses, how our understanding of fundamental things and the constants linked to them evolves through, intense debate, clever experiments, and theoretical breakthroughs. It took centuries to figure light out.
So what was the big debate?
For a long, long time, the central question was, is light made of particles or is it a wave? Isaac Newton himself championed the particle idea. His corpuscular theory proposed light consisted of tiny particles, or corpuscles.
And that explains some things.
Oh yeah, it worked well for explaining reflection light bouncing off mirrors and refraction light bending when it goes through, say, water or a prism. Think about how a prism creates a rainbow. Newton explained that by corpuscles of different colors bending by different amounts.
Okay, so particles seemed plausible, but there was another view.
Yes. Christian Huygens, a contemporary of Newton, argued strongly for light being a wave. He thought of light spreading out from a source like ripples on a pond, creating wave fronts.
Particle versus wave. What evidence started tipping the scales?
Key experiments began to favor the wave theory. One crucial phenomenon was diffraction. That's the tendency of waves to bend when they pass through a narrow opening or around an obstacle.
Like sound bending around corners?
Exactly. If light were just particles traveling in straight lines, you'd expect really sharp shadows. But careful observation showed light does bend slightly around edges, creating fuzzy shadows. The corpuscular theory struggled to explain that easily.
Yeah, interesting.
But the real nail in the coffin for the simple particle theory, at least for a while, was Thomas Young's double-slit experiment in the early 19th century. This is a classic.
I think I've heard of this one.
Probably. Young shone light onto a screen with two very narrow parallel slits cut into it. Now, if light were just particles, you'd expect to see two bright lines on the detector screen behind the slits, corresponding to the particles that went through either slit A or slit B.
Makes sense.
But that's not what he saw. Instead, he observed an interference pattern, a series of alternating bright and dark bands, or fringes. This is classic wave behavior. Where the crests of the waves from both slits meet, they add up, constructive interference, bright band. Where a crest meets a trough, they cancel out, destructive interference, dark band.
Just like water waves interfering.
Precisely. It was incredibly strong evidence for the wave nature of light. Later, Augustin Jean Fresnel developed the wave theory mathematically with great precision, explaining diffraction and other optical effects quantitatively. So for much of the 19th century, the wave theory reigned supreme.
But the story wasn't over, right? Quantum mechanics brought particles back.
Exactly. That's the fascinating duality. Later physics showed light does behave like particles,
Yeah.
photons, in some contexts, like the photoelectric effect Einstein explained.
Yeah.
But the 19th century work firmly established its wave properties and set the stage for understanding its speed.
Okay, so light is behaving like a wave. How did we get to its speed being a fundamental constant? That seems like a bigger leap.
That leap came through unifying electricity and magnetism. It was a truly profound moment in physics. It started with the experimental work of Michael Faraday in the mid-19th century.
Faraday, right. Electromagnetism.
He discovered deep connections. He showed that a changing magnetic field could induce an electric current in a wire that's electromagnetic induction, the basis for generators. And conversely, electric currents create magnetic fields. There was this intimate link, but the full picture wasn't clear yet.
It needed a theory to tie it all together.
And that theory came from James Clerk Maxwell. Around the 1860s, he brilliantly synthesized everything known about electricity and magnetism into just 4 elegant equations. Maxwell's equations. They are cornerstones of modern physics.
What did they show?
They described all electrical and magnetic phenomena known at the time. But they did something even more astonishing. They predicted the existence of waves made of oscillating electric and magnetic fields traveling through space. Electromagnetic waves.
Okay, so waves were predicted.
But here's the mind-blowing part. Maxwell could calculate the speed of these predicted waves directly from his equations, using constants related to electric and magnetic forces that were already known from lab experiments.
And the speed he calculated.
It precisely matched the experimentally measured speed of light.
Wow.
It was an electrifying moment. The inescapable conclusion was that light itself is an electromagnetic wave. It wasn't just some separate optical phenomenon. It was a fundamental manifestation of electromagnetism.
So c wasn't just the speed of light, it was the speed of electromagnetism.
Exactly. It cemented C as a truly fundamental constant, deeply embedded in the laws governing electricity, magnetism, and light.
And people had tried to measure the speed of light before Maxwell, right? It wasn't thought to be infinite.
Correct. For a long time, people thought light might travel instantaneously. But Ole Rummer, a Danish astronomer, made the first good quantitative estimate way back in the late 17th century.
How did he do that?
He was carefully observing the eclipses of Jupiter's moon Io. Io orbits Jupiter relatively quickly, so its eclipses, when it passes into Jupiter's shadow, happen frequently and predictably. Romer noticed that the timing of these eclipses seemed to vary throughout the year.
How so?
They appeared to happen later when Earth was farther away from Jupiter in its orbit and earlier when Earth was closer. Romer correctly deduced this wasn't due to Io changing its orbit, but because the light from Io had to travel a greater distance to reach Earth when the planets were farther apart.
Ah, the travel time of light.
Exactly. Based on the observed delay and the estimated size of Earth's orbit, he calculated a finite speed for light. His value wasn't perfectly accurate by modern standards, but it was a first solid proof that light does have a finite speed, and it was in the right ballpark. It disproved the idea of instantaneous propagation.
Okay, so light is an electromagnetic wave traveling at a finite fundamental speed, c. Then comes Einstein. How did he change our view of c?
Einstein took the constancy of c and made it the absolute bedrock of his new physics. You see, while Galileo's principle of relativity worked well for everyday speeds, it started to break down when applied to Maxwell's electromagnetism. There were inconsistencies. Yeah, like Maxwell's equation seemed to imply the speed of light should be the same, regardless of how the source or the observer was moving, which contradicted Galilean relativity, where velocities simply add up. People like Hendrik Lorentz developed mathematical transformations, the Lorentz transformations, to try and reconcile this, showing how measurements of space and time might need to change for observers moving at high speeds relative to a hypothetical ether that light supposedly traveled through.
So they were trying to fix the existing framework.
Pretty much. But Einstein, in 1905, with his special theory of relativity, took a much bolder step. He basically threw out the idea of the ether and proposed 2 fundamental postulates. One was that the laws of physics are the same for all observers in uniform motion, extending Galileo. The other, revolutionary postulate, was that the speed of light in a vacuum, c, is the same for all inertial observers, regardless of the motion of the light source or the observer.
He just declared c to be absolutely constant for everyone.
Yes. He elevated it to a fundamental principle of nature. And the consequences of accepting this constant speed of light are truly profound and, frankly, weird.
Like what? This is where space and time get warped, right?
Exactly. The invariance of C forces us to abandon the classical notions of absolute space and absolute time. It leads directly to experimentally verified effects like time dilation. Time literally passes slower for objects moving at very high speeds relative to a stationary observer.
That actually happens.
Oh, absolutely.
Yeah.
Particle accelerators see it all the time. Unstable particles moving near seats live longer than identical particles at rest. And it's crucial for GPS satellites. Their clocks run slightly faster in orbit due to lower gravity, that's general relativity, but slightly slower due to their high speed, special relativity. We have to account for both effects precisely for GPS to work accurately.
Wow. Okay, what else?
Length contraction. Objects appear shorter in their direction of motion when observed by someone they are moving relative to, especially at speeds approaching c. Yep. And of course, the most famous one, mass energy equivalence, EMC in chair. This equation shows that mass and energy are fundamentally interchangeable. Mass is a form of concentrated energy, and c squared is the enormous conversion factor, which explains why nuclear reactions release so much energy from a tiny amount of mass.
Okay, so C isn't just a speed limit, it connects mass and energy too.
And it is the ultimate speed limit. For anything with mass, any information, c is the cosmic speed limit. As you approach the speed of light, it takes more and more energy to accelerate you further. Your relativistic mass increases, making it infinitely hard to actually reach c. It's an insurmountable barrier built into the fabric of space-time itself. It defines causality effects cannot happen before their causes because no signal can travel faster than light.
So we have these incredibly important constants like C and G, but you mentioned earlier how even our definitions of basic units like the meter have changed to relate to them. How does that work? How have our measurement standards evolved?
That's a really crucial point, because how we define our units is deeply tied to how accurately we can know these constants and our desire for truly universal standards. It's a fascinating story of moving away from arbitrary physical objects towards using the constants themselves as the definition.
Making the definitions based on the universe, not us.
Exactly. Let's take the meter. Originally, back in revolutionary France, 1791, it was defined geopolitically as 1/10,000,000th of the distance from the North Pole to the equator, passing through Paris.
That sounds hard to measure accurately.
Extremely. So later, they made a physical artifact, a bar made of platinum iridium alloy, kept in a vault near Paris. That bar was the meter. Copies were distributed, but the original was the standard.
Okay, a physical object.
But physical objects have problems. They can expand or contract with temperature. They can get damaged. Maybe they even change slightly over decades. It wasn't truly universal or unchanging. So in 1983, a major shift happened. The meter was redefined based on the speed of light. The modern definition, set by the BIPM, International Bureau of Weights and Measures, is the meter is the length of the path traveled by light in a vacuum during a time interval of exactly 1 divided by 299,792,458 of a second.
Whoa, so they fixed the speed of light.
Precisely. By defining the meter this way, the speed of light in a vacuum, c, becomes an exact defined value, 299,792,458 meters per second. No uncertainty. It's no longer something we measure with increasing precision. It's a fixed number that defines the meter. The uncertainty now shifts to how well we can realize the meter in practice based on measuring time, which we can do incredibly accurately with atomic clocks.
That's a huge conceptual shift. What about the kilogram? That was that cylinder in France too, right?
Yep, le grand K. For over a century, the kilogram was defined by that specific platinum iridium cylinder. All other masses were ultimately compared to it or its copies. But again, physical artifact problem. Studies showed its mass was actually drifting slightly compared to its copies over time. Exactly. So this prompted another major redefinition, which just happened quite recently in 2019. The kilogram is no longer defined by le grand K.
So what defines it now?
It's now linked to another fundamental constant, Planck's constant h.
The quantum constant. How do you define mass using that?
It's done using a sophisticated device called a Kibble balance, formerly known as a Watt balance. It's complex, but essentially it precisely balances the weight of a test mass against an electromagnetic force. By measuring the electrical power needed to create that force and relating it to Planck's constant through quantum electrical effects, you can define the mass in terms of h.
Okay, that sounds complicated but fundamental.
It is. The key takeaway is the kilogram is now based on an unchanging constant of nature, h, which has a fixed numerical value, just like c. It makes the definition truly universal and stable.
And the second, how did that change?
The second also evolved away from physical phenomena. Originally, it was based on astronomy, a fraction of the mean solar day, the time it takes Earth to rotate.
But the Earth's rotation isn't perfectly constant.
Exactly. It slows down very slightly over time due to tidal forces and has small irregularities. As our clocks got better, we needed more stable reference. So in 1967, the second got its atomic
The
definition.
atomic clock.
Right. The second is defined as the duration of exactly 9,192,631,770 periods of the radiation, corresponding to a specific transition between two energy levels, the hyperfine levels of the ground state of the cesium-133 atom.
Okay, say that again slowly.
Basically, cesium-133 atoms have electrons that can flip between two very closely spaced energy states. When they flip, they absorb or emit microwave radiation with an incredibly precise and stable frequency. We count 9,192,631,770 cycles of that radiation, and that's 1 second. It's astonishingly precise.
So light speed c and Planck's constant h are now defined values, and the second is defined by atomic transitions.
Correct. These are now definitional constants in our modern SI system of units. Their numerical values are fixed by definition. It only makes sense in the context of the units we use, meters, kilograms, seconds. It shifts the burden of measurement accuracy onto realizing those units based on these fundamental definitions.
It really does feel like these constants are the language of physics, the bedrock.
They really are. From a physics perspective, they're more than just numbers. They are, as the book calls them, both pillars and essential and determining characteristics of the physical laws. They underpin everything.
Like c being the ultimate speed.
Exactly. Or defining the scale of quantum affects the granularity of the universe at small scales. These constants are intrinsically linked to the natural quantities and limits within physics. And as physics progressed, especially with relativity and quantum mechanics, we realized they aren't just arbitrary numbers we measure. They seem deeply embedded in the structure of reality itself. Our perception shifts from them being just measured values to being fundamental principles.
Okay, this is where it gets really wild for me. If they're so fundamental, so embedded, is it possible they aren't truly constant? Could they change over time or be different in other parts of the universe?
Now you're asking the really deep, cutting-edge question. That possibility that the constants might not be constant is incredibly provocative. It challenges the very foundations of our current understanding.
It would be huge if they varied.
Monumental. It's an active area of research, pushing the absolute limits of experimental precision. Physicists are searching for the faintest hint, the tiniest whisper of change.
Why are the stakes so high? What would it mean if they did vary?
Well, if a fundamental constant were definitively found to change, it would fundamentally challenge the completeness, maybe even the correctness, of our current physical theories, like general relativity or the standard model of particle physics. These theories assume that constants are constant.
So the theories would be wrong or incomplete.
Incomplete, most likely. It would imply that the laws of physics themselves might be evolving, or that there's a deeper theory we haven't discovered yet that governs why they might change. It would have profound implications for cosmology, our understanding of the universe's history, its future, maybe even its origin, as part of this quest to see if our current physics is the final word, or just a really good approximation.
So how on earth do you test something like that? How can you tell if, say, the strength of gravity was different billions of years ago?
That's the challenge. One of the most powerful tools we have is astronomy. By looking at very distant objects, we're essentially looking back in time, because the light from them has taken billions of years to reach us.
Using telescopes as time machines.
Pretty much. We can analyze the light from distant galaxies, and especially quasars, which are incredibly bright, active galactic nuclei.
How does analyzing their light help?
We use spectroscopy. Light from a distant quasar often passes through vast clouds of intergalactic gas on its long journey to Earth. Atoms and ions in those clouds, things like hydrogen, carbon, silicon, iron, absorb very specific wavelengths of the quasar's light.
Creating absorption lines in the spectrum.
Exactly. You see dark lines in the rainbow spectrum of the quasar light at very precise wavelengths corresponding to the elements in the cloud. Now, the exact wavelengths of these absorption lines depend crucially on the values of fundamental constants,
Which ones?
particularly the fine structure constant, alpha. Alpha governs the strength of the electromagnetic interaction, which determines the energy levels within atoms and therefore the exact wavelengths they absorb.
So if alpha was different back then.
Then the spacing between those energy levels would be different, and the pattern of absorption lines we see from that ancient gas cloud would be slightly shifted compared to the pattern we measure in labs today. It's a very subtle shift, mind you, distinct from the cosmological redshift caused by the expansion of the universe. You need incredibly precise measurements.
Has anyone seen such a shift?
There was some excitement in the early 2000s. A team led by John Webb, using the Keck telescope and later the Very Large Telescope, VLT, reported evidence suggesting that alpha might have been slightly smaller by about 6 parts per million, a tiny fraction of a percent in the very early universe based on quasar observations.
6 parts per million. That's tiny, but potentially huge news.
Exactly. It caused quite a stir. If confirmed, it would have been revolutionary. However,
There's a however.
there is. Subsequent studies using different telescopes, different quasars, and refined analysis techniques have largely not confirmed that variation. Most other groups found results consistent with no change in alpha over cosmic time.
So the evidence is contradictory.
It leaned heavily towards no variation. For instance, a large study using the UVES spectrograph on the VLT looked at many quasars and concluded in 2012 that any variation in alpha was less than 0.1 parts per million over billions of years. So much tighter limits, consistent with zero change.
So the current thinking is probably no change based on quasars.
The consensus from quasar data is overwhelmingly towards stability. Yes. The focus now is on improving precision even further, ruling out subtle systematic errors in the measurements, things like tiny calibration drifts in the spectrographs or atmospheric effects. But so far, the universe looks remarkably constant from afar.
Okay, that's looking deep into space and time. Are there ways to test this closer to home, here on Earth, maybe more precise tests?
Yes, absolutely. Terrestrial experiments offer complementary and often even more stringent tests because we can control the conditions much better. 2 main approaches stand out: using ultra-precise atomic clocks and studying a remarkable natural phenomenon, the Oklo natural nuclear reactor.
Let's start with atomic clocks. How do they test constants?
We talked about how the second is defined by the cesium-133 atomic clock, counting those microwave oscillations. Now imagine you build different types of atomic clocks based on transitions in different atoms, say rubidium or strontium or ytterbium.
Okay, clocks using different atoms.
The exact frequency of the ticks in these different clocks depends on fundamental constants in slightly different combinations. For example, the ratio of a cesium clock's frequency to a rubidium clock's frequency depends on alpha, the fine structure constant, the ratio of the electron's mass to the proton's mass, and nuclear magnetic moments.
Ah, so if those constants change.
Then the ratio of the frequencies of the 2 different clocks would drift over time. If you run these different types of clocks side by side for years and compare their ticking rates with extreme precision, you can look for any tiny change in that ratio.
And what have they found?
Astonishing stability. Current comparisons, for instance, between cesium and rubidium clocks showed that the ratio of their frequencies has varied by no more than about 1 part in 10 to the 16 over several years. That's like measuring the age of the universe to within a fraction of a second. It puts incredibly tight limits on any present-day variation in combinations of fundamental constants.
1 part in 10 quadrillion. That's stable.
It's extremely stable. Now, for looking much further back in time using terrestrial evidence, we have Oklo.
Oklo. What's that? You said a natural nuclear reactor.
It sounds like science fiction, but it's real. In the Oklo region of Gabon, in West Africa, geological conditions about 2 billion years ago were just right for natural nuclear fission reactions to occur spontaneously within uranium ore deposits.
How is that possible?
Well, 2 billion years ago, natural uranium contained a significantly higher percentage of the fissile isotope uranium-235, about 3.7%, compared to today, only 0.7%. This higher concentration, combined with groundwater acting as a moderator to slow down neutrons, allowed sustained nuclear fission chain reactions to start and run intermittently for hundreds of thousands of years. It was literally a natural nuclear reactor operating deep underground.
That's incredible. How does it help test constants?
It provides a unique fossil record. One key process in the reactor was the fission of U-235 producing neutrons. Some of these neutrons were then captured by other elements present in the ore. One particularly important element is samarium-149. SM-149. Samarium-149 is very effective at capturing thermal neutrons. The probability of it capturing a neutron, its capture cross-section, is extremely sensitive to the value of a specific nuclear interaction parameter that depends on the strength of the strong nuclear force, often related to the fine structure constant alpha, but more directly prodding the nuclear forces themselves.
So the S-149 abundance today tells us something.
Exactly. If the strength of the strong force, or related constants like alpha, had been different 2 billion years ago, the neutron capture rate by SEM-149 would have been different. This would have resulted in a different final abundance of SEM-149 relative to other samarium isotopes in the Oklo ore samples that we analyze today.
And what did the analyses show?
Pioneering work by Schleiermacher back in the 70s, and later refined analyses by people like Damore and Dyson, looked at these isotopic ratios. They concluded that the relevant nuclear constants, and by extension alpha, could not have varied by more than about 1 part in 10 million, 10 to 7, over the last 2 billion years.
1 part in 10 million over 2 billion years.
It's an incredibly tight constraint, coming from right here on Earth, looking deep into the past. It strongly complements the quasar and atomic clock data.
So putting it all together, quasars, atomic clocks, Oklo, the overwhelming picture is stability.
Yes. Well, physicists always keep looking and refining measurements because finding a variation would be Nobel Prize-worthy stuff. The evidence accumulated so far from very different methods probing different eras and different constants points very strongly towards the fundamental constants being truly constant, at least to the remarkable precision we can currently achieve.
Okay, so if these constants are so fixed and their stability seems rock solid, what's the next big question? Is it maybe why they have the specific values they do? Why is IXC 299,792,458 meters? Why is alpha about 1,137?
You've hit on the next frontier, the deeper mystery. If they don't vary, why these specific values? This was something that deeply bothered physicists like Paul Dirac, one of the giants of quantum mechanics. He famously pondered the value of the fine structure constant, alpha roughly 1137. Why that number?
Is it just random? A cosmic dice roll?
That's one possibility, maybe the brute fact possibility. But the ambition of theoretical physics is to go deeper, to explain why these constants have the values they do. Why is the ratio of the proton's mass to the electron's mass about 1836? Can we derive these numbers from some more fundamental theory, rather than just measuring them and plugging them into equations?
The theory of everything. Dream.
Exactly. The quest for a single, comprehensive theory that could potentially explain all physical phenomena and, crucially, predict or derive the values of these fundamental constants from first principles. That's the ultimate goal for many theorists.
Has there been progress towards that? We mentioned Maxwell unifying electricity and magnetism.
That unification was a huge inspiration. It showed seemingly separate forces could be aspects of one underlying reality. Einstein spent years trying, unsuccessfully, to unify gravity with electromagnetism. The current standard model unifies electromagnetism with the weak nuclear force, the electroweak theory. But gravity and the strong nuclear force remain separate in that picture.
So what are the modern ideas for unification?
One influential, though still speculative, direction comes from ideas involving extraspatial dimensions, building on that early Kaluza-Klein concept we touched on.
Right, the idea of a fifth dimension curled up really small.
Kaluza-Klein's original idea in the 1920s was to unify gravity, general relativity, and electromagnetism by adding a fifth dimension. Klein suggested this dimension was compactified, curled up into a tiny circle at every point in our familiar 3D space, way too small for us to see directly.
The ant on the tightrope analogy.
Exactly. From far away, the tightrope looks 1D length. For the ant walking on it, it has a second dimension, the circumference. We might be like the distant observer, only seeing 3 large spatial dimensions, while others are curled up at incredibly small scales.
How would that unify forces?
In the Kaluza-Klein picture, the electromagnetic force essentially emerged as a component of gravity operating within this hidden fifth dimension. The geometry of that extra dimension determined the properties of electromagnetism. It even made predictions, like potential deviations from Newton's law of gravity at very short distances.
Did that theory work out?
Not in its simple original form. It didn't incorporate the other forces, strong and weak nuclear, and had some theoretical issues. But the core idea, unifying forces through the geometry of extra dimensions, has been incredibly influential. It's a central theme in modern theoretical frameworks like string theory and M-theory.
String theory proposes even more extra dimensions, right?
Yes, typically 10 or 11 space-time dimensions in total. In these theories, the fundamental constituents of nature aren't particles, but tiny vibrating strings or higher dimensional objects called branes. The way these strings vibrate and the shape and size of the compactified extra dimensions would determine the types of particles we see and the values of the fundamental constants, including the strengths of all the forces.
So the constants would come from the geometry.
That's the hope. If we could figure out the correct geometry of these extra dimensions, the theory should, in principle, predict the constants we observe. It's a beautiful mathematical idea, but incredibly difficult to test experimentally because these dimensions are thought to be unimaginably small, far smaller than anything we can probe directly.
It also touches on another big puzzle you mentioned, the hierarchy problem. Why is gravity so incredibly weak compared to the other forces?
Exactly. That's one of the biggest mysteries. Why the enormous gap, like 39 orders of magnitude between gravity and electromagnetism? It seems unnatural. Some extra-dimensional theories offer possible explanations. Maybe gravity seems weak because it's the only force that propagates through all the dimensions, including the extra ones, so its strength gets diluted in our 3D perception.
Leaking into other dimensions.
Sort of, yeah. Or maybe its fundamental scale is linked to the size of the extra dimensions. Dirac also had his large number hypothesis, noting strange coincidences between huge numbers in cosmology, like the age of the universe in atomic units, and ratios of forces, speculating that maybe constants change over time to maintain these ratios. But again, evidence for varying constants is lacking.
This also connects to the anthropic principle, doesn't it? The idea that the constants seem fine-tuned for life.
It does, and it's a fascinating, sometimes controversial area. The observation is that if you tweak the values of several fundamental constants, even slightly, the universe would be drastically different and likely couldn't support life as we know it.
We talked about stars and atoms.
Right. Change the strong force strength, and you might get no elements beyond hydrogen, or stars that burn out instantly. Change the electromagnetic force strength, alpha, and atomic structures change dramatically. Change the ratio of proton to electron mass, and chemistry goes haywire. It seems like the constants fall within a very narrow range that allows for complex structures, stars, planets, and ultimately life.
So why this apparent fine-tuning?
That's where the anthropic principle comes in. The weak anthropic principle is less controversial. It basically says, we as observers exist. Therefore, the universe we observe must have properties, including the values of constants, that allow observers like us to exist. It's a selection effect. We wouldn't be here to observe a universe where the constants didn't permit life.
Okay, that makes sense. We can only see a universe we can live in.
Right. The strong anthropic principle goes further and is more philosophical. It suggests the universe must have properties that allow life to develop within it at some stage. This hints at some underlying purpose. Or maybe that our universe is just one of many in a multiverse.
The multiverse idea.
Yes. If there are countless other universes, perhaps each with different random values for the fundamental constants, then it's not surprising that we find ourselves in one of the rare universes where the constants happen to fall within the narrow life-permitting range. We simply couldn't exist in the others.
So it's either fine-tuned by design, a brute fact, or we just live in a lucky universe among many.
Those are the main lines of thought. It highlights how the values of these constants push up against some of the biggest questions in physics and cosmology, bordering on philosophy. Why are things the way they are?
So where does this leave us? We've seen constants are pillars of physics, incredibly stable, yet their precise values are a deep mystery hinting at unification or maybe even multiverses. What's the focus now? Where do physicists go from here?
Well, the quest definitely continues on multiple fronts. On the experimental side, the search for any tiny variation in constants goes on with ever-increasing precision. We're constantly building better atomic clocks, designing more sensitive spectroscopy methods for quasars, looking for subtle effects in lab experiments.
Still hoping to find that tiny crack in the constancy.
Or, more accurately, to push the limits of stability ever further. Because even setting tighter limits is valuable information. It tells us just how robust our current theories are, or constrains the possibilities for new theories beyond the standard model or general relativity.
And finding even a tiny variation wouldn't break physics.
Not break it, no. It would revolutionize it. It would be the signal that our current understanding is incomplete, that there's a deeper layer, a grander theory waiting to be discovered. It would point the way towards that new physics. So researchers are keenly comparing different types of atomic clocks, analyzing light from the most distant objects, trying to spot any deviation, however small, within the realm of what's actually measurable.
And on the theoretical side, the quest for unification continues.
Absolutely. That's the driving force for much of theoretical particle physics and cosmology, trying to bridge the gap between gravity, general relativity, and the quantum world of the other forces, the standard model.
Extra dimensions, string theory, are those still the main contenders?
They remain very active areas of research. The idea that the fundamental forces might arise for the geometry of hidden extra dimensions is still compelling to many physicists. It offers a potential path to unification, and maybe even explaining the hierarchy problem, why gravity is so weak. Perhaps, as we discussed, gravity spreads its influence through more dimensions than the other forces.
Trying to explain everything from geometry.
That's the allure. A theory where the particles, forces, and constants all emerge naturally from the fundamental structure of spacetime, perhaps including these extra dimensions. Experimentalists are also trying to probe this indirectly. For example, by testing Newton's law of gravity at very, very short distances micrometers, or even less, to see if it deviates in a way predicted by some extra-dimensional models.
A huge challenge, given the scales involved.
An immense challenge. Many of these theories operate at energy scales far beyond what current particle accelerators like the LHC can reach directly. So physicists look for subtle, indirect clues or hope for breakthroughs in experimental techniques or astronomical observations. It's a long game, driven by these fundamental questions about the constants that define our universe.
So let's recap this deep dive. We started by defining these fundamental constants, unchanging numbers like C, G, H that underpin all of physics.
The pillars of reality, really.
We journeyed through history, seeing how Kepler, Galileo, and Newton laid the groundwork, how the debate over light as particle or wave led to Maxwell unifying electromagnetism and revealing EC's fundamental nature.
And how Einstein built relativity on the absolute constancy of C.
Then we saw how our very units of measurement, the meter, the kilogram, the second, have evolved to be defined by these constants, making our standards truly universal.
Moving from physical artifacts to fundamental physics.
And we tackled the big question. Are they really constant? Looking at evidence from distant quasars, the Oklo natural reactor, and ultra-precise atomic clocks.
All pointing overwhelmingly toward incredible stability over billions of years, down to phenomenal precision.
Which leaves the profound mystery, why these specific values? Leading us to the grand ambition of a unified theory, maybe involving extra dimensions and confronting puzzles like the hierarchy problem and the anthropic principles fine-tuning argument.
The frontiers of theoretical and experimental physics today.
So, as we keep refining our measurements and our theories, the really big question hangs there. Are the values of our fundamental constants just brute facts of our particular universe, a lucky draw? Or are they inevitable consequences of some deeper, yet-to-be-discovered theory of everything that will finally explain why they are what they are? And here's a final thought for you to mull over. If one day we could somehow confirm the existence of a multiverse where these constants do take on different values in other universes, how would that change our understanding of what it even means for a law to be natural or universal?
It really makes you think, doesn't it?
It challenges us to consider that perhaps the greatest constants aren't just the numbers in our equations, but maybe the ceaseless human curiosity that drives us to ask these questions and the universe's unending capacity to surprise and inspire wonder.
Well said. The search definitely continues.